So thank you very much for the introduction. I want to start by thanking the organizer for giving me the opportunity to talk here, and especially Dr. for making me coming here, because I had some, I was not sure how to organize. And so I am I'm Lauriane Chomaz. I was a postdoc, in fact, in a group of Francesca Ferlarino in Innsbruck between 2015 and 2020. And I just started as a tenure-track professor in Heidelberg University 1 year ago. And so as a disclaimer, I'm more a many-body person, I would say. And I should say that in the last few days, I've been thinking what was the most beneficial for me to present here to you and to talk to you. And that's why I changed my title to a bit broaden my the scope of my talk finally. So, okay. Sorry. I'm sorry. Okay. Yeah. So yeah, what I want to discuss with you is first I will try to give you a quite broad, let's say, overview of our platform, which is ultra-cold gases made of magnetic atoms, and also especially in the few body perspective. Then I will discuss a few of the main results that we got, in particular in Innsbruck over the last 5 years, and in particular toward this quantum stabilized state. And I will shortly discuss also my new experiment in Heidelberg. And so first to introduce this platform of magnetic atom, I want to go back for your perspective, let's say, to really a basic thing of scattering theory in the ultra-cold and dilute regime. And the first point is to say that, let's say, all the interaction that decay fast enough with the distance between the particle can be approximated in this regime of ultra-cold interactions, ultra-cold regime into a compact pseudo-potential. This is, but it's only described by this kind of delta potential and parameterized by a unique parameter, which is the S-wave scattering length. And this is because only the S-wave partial wave have a non-vanishing, let's say, phase shift in this ultra-cold regime. So this is true for potential that decay fast enough, and fast enough is n to larger than n over n3. And this is in particular the case for the van der Waals interaction, which are the dominant interaction in most of the atomic species, which is R to the 6 because it's induced by the induced electric dipoles between the atoms. And this description has been really powerful. It's really, let's say, a simple description, but it has led to a lot of really nice results, and also there is all this universality that are deduced from this. However, like the interaction that you can do in between the particles due to this potential is still rather limited in its variety, and that's why, let's say, people have been interested into going towards other kind of potential, and that's where comes the idea of dipolar interaction, because here you will have a power of n equal to 3. So, yeah, that's somehow the dipolar potential that we will be interested in, and decay, as I said, as a power of 3. And it is also anisotropic into the orientation of the dipole and the interparticle distance. And there are different platforms where you can have this dipolar interaction, and the one I'm interested in is the one where we use the, let's say, the natural magnetic dipole moment of the atoms. So that's only due to their constant electronic configuration. And you can see in this periodic table, encoded by the coder from blue to red, the dipolar length, which is coming here, and which is setting the strength of this interaction. And you can see that there are some atoms that have with strong dipolar properties, but they are not the ones that have been cooled first. So the ones that have been cooled first are among the alkalis mostly, but there have been an effort. So in yellow, what is highlighted are the species that have been both condensed in time. And you see that in particular, since 2011 and 12, there have been an interest into this family, which is called lanthanide, and which has the strongest of the magnetic moment among the table. And that's the typical dipolar length for these atoms. And the specificity of these species is due to their electronic configuration with a 6s shell, which is filled, and below there is a 4f shell that have vacancies. And so this gives rise to a large spin among the large effective spin, let's say, which is of electronic origin, and then therefore of a large magnetic moment, and also of electronic transition that can be used for laser cooling, and that's why it has been both condensed. And again, still on this side, I want to highlight that, okay, there is a large spin, but here the interaction that I'm describing is in fact not involving really this spin. So we are considering a state that is fully spin polarized in the lowest state, and there is interaction that are only elastic, so only, let's say, mu z in a sense. Okay. And the interest in this kind of species is not only because it's easier to condense, but also that you have not only this kind of interaction, which is the dipolar interaction, but also the standard van der Waals interaction. And this gives rise to the standard contact kind of interaction. And it has been shown that you can describe this interaction via the pseudo potential, which is just the sum of this contact plus the dipolar one. So that's for bosons, no? And at the background level, for this kind of species, that's really interesting because it's these two kind of interaction are roughly of competing strength, or let's say of the same order of strength. And again, a nice property of the ultra-cold gases platform is that we can also, in this case, tune the interaction using what is called Feshbach resonances. So just by changing the value of let's say, of the uniform magnetic field that we apply on our system. And by tuning this scattering length, the S wave, we can tune effectively the dipolar character of our system at the many body level, let's say. So that's what I will be interested in. I want just to make a small detour before going to this part that is the consequence of this at the many body level, to the, let's say, few body scattering of this atom that are lanthanides, and the specificity that are coming from this. And it has been already a bit mentioned earlier in the conference. And there are several, let's say, specific property to this scattering. And it's quite well encompassed in this plot, which is an experimental measurement of trap loss spectroscopy. If you keep the atom in the trap for a given time at different magnetic fields, and each of these features that are losses, finally, they correspond to one of these Feshbach resonance. And you see that here, in this magnetic field range, which is quite limited, you have a lot of these resonances. And these connect to some exotic property of the scattering of the atom. And mostly, the point that is important is that you have many channels because you have a large spin, and you have also a strong coupling compared to alkali atom between this channel due to the anisotropic interactions. So this has been studied, let's say, in the early days of this lanthanide atom, and in particular in this paper that we finished when I just arrived in Innsbruck, we studied a bit the contribution of the different part of the anisotropic interaction. And in particular, there is not only the dipolar interaction, which is anisotropic in this atom, but also let's say the C6 has an anisotropic contribution because you have this 4F that have vacancy, and then you have also a dependence of this induced electric dipole on the orientation of the interaction compared to the polarization magnetic field. And we have studied the contribution of these two terms, let's say, with our theory collaborators. And somehow it's encompassed here in the plot of this molecular level close to dissociation at zero magnetic field. So when you apply a finite magnetic field, they will drive to dissociation, and they correspond to then Feshbach resonances. And you see that, so in this plot, we switch off this term, and we only look at the dipolar contribution. And in this plot, we switch off the dipolar term, and we look only at the C6 contribution, let's say, switching on slowly the contribution. And we saw that in this case, the anisotropic Van der Waals was driving, let's say, a lot of hybridic crossing, and then, let's say, a lot of complexity in this Feshbach spectrum. So yeah, that's one point. So we have a lot of this Feshbach resonance. That's really helpful in the experiment. We can easily tune the short-range scattering, even at low magnetic field. But it's also associated, as you could have understood, to a lot of challenges for the theorists also, but also to know what are exactly the scattering properties in this system. In particular, just the scattering length is not so clear. And also there are some experimental challenges because the use of this let's say, we can only use relatively narrow resonance because for the resonance, there are a lot of different narrow resonance that are on top of them. I just want also to highlight a more recent paper that we did again with a group in Innsbruck, where we tried to understand better these low field scattering properties. And in particular, we compare different methods to extract the scattering length and also look at, let's say, the different isotopes and the isotope scalings. Okay, so that was a little detour, but I'm also happy to discuss this with you later on. Now, for now, I will only use, let's say, the opportunity of this few body physics and use the fact that we can tune this scattering length. And so I go back to this plot where we have competing of these two kinds of interaction. And what I would like to show you now is in a many-body state, where this can lead to a particular feature. And in particular, the two features that I want to discuss is the fact that you can have a quantum stabilization of a mean field attractive system and a self-organization which will be of tunable strength. And I want to show then finally what this led to new many-body behavior, and in particular supersolids. So for the first part, the quantum stabilization, it was well known in our community, let's say, but let's say Bose-Einstein condensate. So it's only stable if you have somehow mean field repulsion. And if you tune the interaction to be mean field attractive, what happens is that you have no finite stable state. And when you drive this transition, you will induce a fast implosion and explosion, which was described as Bose-Nova in the system. And you have a very fast loss of the atom with like the creation also of really interesting density patterns. And this is true, like it has been shown really early on for alkali bases, but also for moderately dipolar system like chromium. And an important discovery in our field was done in 2015 in the group of, 2016, in the group of Tillman 4 in Stuttgart. And what they saw is that they tried to do this kind of experiment with dysprosium. And they saw that they don't have this really fast loss of on the scale of below a millisecond, but they have a relatively stable state that live like hundreds of milliseconds, but that form this density pattern that are really dense. So this is in situ images, and you have this, let's say, this blob of density that are appearing. And at this point, it was not understood at all why this was coming from. And there were different theory and the debate, and it was finally understood that this arrived from the quantum stabilization effect. And this is based on the seminal work by Dima Petrov that was nearly at the same time as this experiment, in fact. I want just to describe to you really briefly what is the idea behind this. And the point is that, okay, we go to a system that is really close to instability. So we tune the mean field interaction to be nearly zero. But this is done in our system with two competing interaction, one which is the contact and that is strongly repulsive, and one which is the dipolar interaction, which in average in the system, let's say at the mean field level, is strongly attractive. So in average, the system is not interacting, but the interactions are still relatively strong for, let's say, in absolute value. And then what comes into play is that there are still interactions. So BC is not this only this mean field term, but if you have a view, let's say many body, you can see it as a field which is a class, let's say a mean field part and a fluctuating part, and there remains this interaction with the fluctuating part. And what is nice is that in, let's say in our system, we can treat this perderivatively and look only at the first order. And this was done early on by Li Wang and Yang, and calculated also for the case of dipolar interaction by Dima and Pelser. And this has a really simple form, and the characteristic point is that it's scaled with a larger power of the density, and it's always repulsive at this first order. So this means that you will have an additional energy contribution, which is stabilizing larger density states. So in particular, if you drive the system to be slightly mean field attractive, what happens is that the collapse will start, the density will increase, and at some point this term will become dominant and stabilize the system. So that was the idea, and that was what led to this stabilization. And then further on, there have been several studies. In particular, in his book, we did some study on the erbium single droplet, on this new kind of state, which are somehow many-body bound states. So that's what I wanted to say about this quantum stabilization. And now I would like to go to the self-organization part. And to have a look into this, what I want to do is to go back to, let's say, the dispersion relation on top of a many-body state. And this somehow describes, let's say, what are the elementary excitation, or the energy of this elementary excitation, with a given momentum, which corresponds in a, let's say, in a really rough picture, to a density modulation with this spatial period, which is related to the inverse of this momentum. And this idea of this elementary excitation and the dispersion relation, it goes back to, in fact, to early work by Landau to describe the specific property of liquid helium and superfluid helium. And in particular, what Landau highlighted in that there are some of these elementary excitation that have low energy. So there is this phonon branch, which relate to the speed of sound. And also this minimum here at finite momentum, which he called the roton. And it was highlighted not by him, but later on by Feynman, but this roton indicates a tendency of the system to crystallize. And you can see this because somehow it costs less energy to excite this specific density modulation. So if you could drive this minimum to zero, you will tend to form a crystal at this wavelength. So now what about our quantum gases and this dispersion relation? So what is really nice is that in our system, again, we can do perturbative treatment, and the dispersion relation in this perturbative treatment, like what I call Bogolyubov, you can see that the energy of this elementary excitation is mostly a kinetic term and a term that comes from the interaction. And this term that comes from the interaction is roughly, let's say, just the Fourier transform of the interaction potential. So what does it give for the case of a contact gas? Because you have a delta potential for like in real space, you will have only a constant contribution for all the excitation from the interaction, and you will not have a roton. So you will have something that evolves mostly from phonons to quasi-particle. So that's the, let's say, the interest also to go beyond this just contact interaction to have some more complex contribution and more complex spectrum of excitation. And in particular, this can be done with dipolar interaction, but in fact, not only with dipolar interaction, but also what we need is an anisotropic confinement, and in particular, a strong confinement along the dipole, because the contribution of a dipolar interaction without confinement will be only dependent on the orientation of the momentum and not on this norm. So to have a roton, we need this additional confinement to recover dependence in this mode. And to give maybe a more intuitive picture on this effect of, let's say, of the anisotropic of the interaction and on the confinement. So now we consider, let's say, a tube like this, and that have a transverse length LZ. So if we look at the small momentum, so a long wavelength, if we see like the density modulation that is induced by this excitation, it's mostly elongated along the dipole. So the contribution of the interaction, of the dipolar interaction, is mostly repulsive, and it will increase the energy of excitation. And now if, let's say, if you increase the momentum and reduce the modulation length to a point where it becomes, let's say, on the order or smaller than the transverse length, then the density modulation will be more and more elongating along the dipoles. And this will lead to an attractive contribution. And that's why we can have this minimum here. Now, again, what is very interesting in our system is that we don't only have this dipolar contribution in the contribution of the interaction, but also this additional constant, which is the S-wave scattering length. And this one we can tune. So what this leads is that we can tune really the value of the gap of the roton down to 0 and even to imaginary. And this we have shown, in fact, in Innsbruck in 2 sets of experiments. I will not give you the detail, but one we did by doing some bright spectroscopy, similar to what is done in helium, but now with photons. And we measured the response of the system, which is just a resonance, and we extract the resonance. And by this way, we extract the dispersion relation, and we see the appearance of this minimum. And we did, in fact, an earlier experiment where we probed also the existence of the roton by doing a quench, and we looking at the population in momentum and the emergence of a population, of a coherent population of this mode. So now I want to combine the 2 ingredients that I told you. So at this point, the self-organization, which is of tunable strength, so let's say the roton, the fact that we can soften the roton, and quantum stabilization. And from this, we can wonder, because this full softening of the roton will also induce an instability. And this instability could maybe be stabilized if there can be new ground states that are not just the BEC or just the droplets. And in particular, if there can be a super solid. So I will not give you a lot of detail, but I just want to highlight. So first, to give you this idea of what is the super solid, it will be a state that have both the property of a solid, so the atoms will tend to localize a certain position of space, and a superfluid, so they will also flow without friction over the full system. And these have been debated for a long time in the community, or let's say, starting from helium, and also, let's say, first negate its possibility, and then a lot of proposition to realize it. It was also searched in experiment for a long time based on solid helium, but in this system, no, it's quite understood that there is not such a super solid. and the fact that we could realize, ultra-cold gases led to a new platform where we could form this super solid. And this will be based on new kind of interaction. So there are all these different platforms, and here I will only describe you the dipolar case. So this was, let's say, it was work that followed all this process of seeing the roton and seeing the quantum stabilization. And there were 3 different experiments, in fact, that realized this in 2019. And first look that you can have into the possibility of this super solid is by looking at mean field theory extended by this possibility of quantum stabilization. And that's what we did in our group. And that's what is represented in this plot, where you have the scattering length and the number of particles. And when we tune these 2 parameters, you see the different states that I already mentioned to you. So first, the BC state, and these 2 droplet states that we saw at the beginning. And what is interesting here is this red region here, which is really narrow in scattering length. And this corresponds to a state where, so here is the density profile of this bound state. And you see that it's not fully modulated. And this not full modulation will mean that you can have somehow a channeling of the atom from one droplet to the other droplet. And so this will correspond to a super solid state. So we were looking into this, into the experiment. It took quite some time because this region is narrow, as I said. So the way we do this in experiment is to look at the self-interference of the state. I will maybe not go too much in detail because I'm a bit late. But mostly what we saw is you will have a signature of the in-situ density modulation because of the presence of interference pattern. And if these interference patterns are reproducible, this will indicate, let's say, the fact that you have a global phase in the system. But if they are not reproducible, this indicates random phases in the density modulation. And if we compare then the average of the individual patterns, then we can know if we have something that is super solid or that are droplets, or if there is no pattern at all, if it is a BEC. And so we did this in the experiment by starting from a BEC and slowly ramping to the final scattering length. And in this way, we identified the 3 regions of this state. So without any modulation, correspond to a BEC, and then it emerged a modulation, which is also remaining in the average, so which is phase coherent, which will be the super solid, and it remained for 1.5 A0 in the scattering length, and then we recover a state which is independent droplets. So that's finished what I wanted to say about the work in Innsbruck, and I want to highlight that it's still an ongoing work where I've been studied a lot of this property of a supersolid and also trying to form more complex structure of this supersolid. And with this, I want to thank the Innsbruck group and all the people that have done the experiment. I was our theory collaborators. And I want just to give maybe a few words on what I am developing now in Heidelberg. So I started a bit more than 1 year ago, and we have been mostly building this lab and, let's say, first furnishing it. And maybe first I want to give you just a few ideas of what I will be interested in, and my special focus will be in low-dimensional physics and on Taylor trap. And why is this interesting is because, let's say, in the many-body physics, low dimension are pretty interesting in the sense that they have different properties than 3D, and especially there is no conventional ordering of the system because fluctuation suppress this ordering. but there are unconventional orders that can occur, and in particular in 2D, you can have this topological ordering driven by a topological defect that bind or unbind. And this relates really strongly on the interaction in the system, and in particular on their range. So I want to look into this kind of system with dipolar interaction or dipolar gases, which have these competing contact and dipolar interactions. I also want to look again into this quantum stabilization, and in particular the effect of the strong trapping and the fact that you could have a change in the scaling of these quantum fluctuation, and then also maybe new phases or more stable phases, different supersolids and so on. I am also interested into looking on the dynamic of this system and the role of this topological defect or scaling variance. And I want also to highlight that certainly there are also interesting few body question or few to many body question, and in this I've been quite influenced by my neighbor Selim Yochim, and also by the discussion here. And in particular, we can ask a lot about quantum fluctuation and supersolidity. When do you have this coming in? Let's say, how many particles do you need for this scaling? And yeah, and also more about scattering. So I will not give you more detail on the experiment that we are planning. I just want to, but we can discuss later if you want. And I just want to show that our current status is we just got a mod in our system, and I want, before thanking you for your attention, to thank the team that have been working with me in Heidelberg since mostly this year. Thank you.
Was an interesting talk. Questions?
You mentioned the transition, I mean, to two-dimension. I mean, the few body dynamics, I mean, with this contact interaction change dramatically from 3 to 2. Do you expect to see some of these effects?
In the few body, you mean?
Yeah, like, for example, the losses. I mean,
yes.
In one case, you have these Efimov peaks, in 2 dimensions don't have. So if you are thinking about
I don't know a lot about this. I could say that one point for the supersolid, for instance, or for this state, one of the main drawbacks is you go to larger density, and then you have a quite fast decay of the state due to 3-body. And maybe you can have a suppression of this 3-body loss, or a slower loss if you go to low dimension. But I think there are not a lot of studies on the detail of this 3-body effect with lanthanide atoms, let's say. At least I don't know.
Other questions or comments? Yes.
Nice talk.
Thank you.
You mentioned this topological, this BKT transition in the end.
Yeah.
Is this for the BEC, or is it some stride phase, or what is it?
Let's say both.
Both.
Let's say it has not been studied in both cases, and I think for both it will be relevant. What I will certainly start with is with a simple superfluid phase. Here you will have you expect the pairing of these vortices that induce this quasi-long range order and superfluid properties. And this has been shown for contact interacting gases. But with dipolar interaction on top, in fact, let's say there are some theory prediction. I'm not sure if there is a theory consensus, because you have 2 effects. You have like that, let's say this pairing, it occurs because you have this logarithm scaling of the interaction of the vortices and of their kinetic energy. So it's a competition between of this entropy, sorry. and it's a competition between entropy and interaction. And if you introduce no long-range interaction, you should break this logarithm scaling. But you have also some screening effect. And let's say, depending on the strength and the range of the interaction, you should have this screening effect and you should recover PKT. But yeah, it's not clear exactly if for this system it applies. So that's for the superfluid, and then let's say it should also apply to supersolid state, I think. But then, so it's really studying the transition in terms of temperature.
Yeah.
And of course, it's interesting if you think like about liquid crystal and so on, like
Exactly.
if you can have no phases. Yeah.
Thanks.
Yeah.
Yes, please.
Yeah, I have a question. Basically, you go between these regimes of droplet, supersolid, BEC. So do the rotational or the superfluid properties change drastically?
The rotational.
The what?
You said the rotation?
The collective modes,
Yeah.
I mean, it's a...
So this has been studied a bit, but not fully. So what we studied in Innsbruck, but also in the two other group of Giovanni Modugno and Tim Alfort, is the lowest lying mode. So you expect if you have a supersolid, so you break two continuous symmetry. So you should have two distinct phonon branches that correspond to two Goldstone modes. And there are signature of these two Goldstone modes. So that's one property that has been studied. The rotation, it will be really interesting because then you could study the superfluid properties. And in the group of Giovanni Modugno, they did some first experiment where they studied the scissor mode, which is also something where you could extract maybe the superfluid density of it. But it's a bit controversial, the interpretation of these results. And what will be even more interesting is to have a vortex inside. And what is interesting, I should say, on the supersolid is, in our case, like, it's a system where you will have, let's say, a condensed fraction that can be 1, let's say at 0 temperature, but the superfluid density will never be 1. It will always be lower.
Other questions or comments? Then I have just a question, and you mainly talked about magnetic dipole interactions. In principle, one could also consider electric dipole interactions. Of course, atoms do not have a permanent electric dipole moment, but you can induce it via an electric field. Would that also be interesting to study?
I don't know exactly the status in this direction. It has been proposed that you can induce it with light. I think there have been some work, but there are some losses induced by this. The most promising platforms for having electric dipole is, in fact, molecules. Like polar molecules of two atoms of different species, and then you can more easily induce an electric dipole with an electric field directly.
Okay, thank you. Other questions or comments?
It seems that this supersolid related to like trap geometry, like it's elongated. But would you also get it in your two-dimensional?
So what you need, as I tried to mention, is that you need a strong confinement along the dipoles. That's the important point. But if it's 1D or 2D in the other direction, it's not important in theory. Like you should, in both cases, have a supersolid. The limitation, of course, in current experiment, at least, is the atom number that you need to get this.
How many atoms? Yeah, I have another question. How many atoms do you have now?
Let's say around 100,000. So if I go back to this, so let's say that's for airbiome. But below this point, let's say you could not have a supersolid. This is for 1D, and it's worse in 2D. So you will need to have larger atom number. But of course, this also depends a lot on the trap. And if you go to really 2 dimensions, and not, this is still a 3D gas in a sense with a shadow trap. If you go to really 2 dimensions, then it's somehow easier because the, let's say the droplet spacing will be smaller. So the size of this droplet will be smaller. So we'll have more, let's say you will have less atom per droplet, so more droplets. And it should be easier to have super solid if you have a stronger confinement. But the drawback is the losses also.
Thanks.
Hey, could you tell about the 2-dimensional droplets? Will it be appear, or it will be destroyed by the fluctuations, quantum fluctuations? Do you have any prediction for that?
Sorry, if I have
2-dimensional droplets?
Yeah.
Do they appear, or do they destroyed by the quantum fluctuations? Is there any prediction for that?
Quantum fluctuations. Let's say there are some. What to say? So there are some prediction about two-dimensional droplets. So to have really the droplet and not the supersolid, what you would need is to have the dipole in the plane. And here, the quantum fluctuation should still stabilize the droplets.
If you orient your, so you can 2 different orientation, right? So if you orient your, if you orient your dipoles along the, pancake prep, then the repulsive interactions should be sort of kick in. So attractive interaction should be kick in, sorry. And so here the next correction should actually be probably applied to see if the 2-dimensional droplet will work or not.
So you will have a contribution, a stronger contribution of attraction of a dipolar interaction, but you still have a contact to compensate it. So it will appear at a larger value of the contact interaction, and I think the quantum fluctuation should still stabilize it. But okay, I should say there are not full prediction of what are the quantum fluctuation correction in 2D and dipolar gases. Let's say, Let's say there are Monte Carlos and there are also mean fields.
Yeah, and sometimes they see stripes and sometimes they see collapse. I mean, there's a phase diagram as a function of the angle and the,
It should be stable. And the last point is what are the effect of thermal fluctuations?
Okay, I think we can close the first part of the morning session. Let's thank the speaker once again.